Hello everyone, welcome to part 2 of the chapter 5 videos where we're going to build on the foundation that we've laid about just the definition of probability and finding some really basic probabilities. Here we're going to start to talk about some more complicated situations, and in particular we're going to introduce the first one of the rules that we will have about finding probabilities. We will have the addition rule, and then we will also have the multiplication rule later. But at the moment, we're going to stick with the addition rule because whether the addition rule comes into play or not, it's going to be based on whether two events are disjoint. And there's another word for disjoint, which is called mutually exclusive. These are two events that absolutely cannot occur at the same time. So that would be something like when you're flipping a coin, you have this outcome of heads and you have this outcome of tails. And there's no chance whatsoever that heads and tails will happen together. It's going to be either one or the other. And we have here a special addition rule. It's not the general one. We have a special addition rule which comes into play whenever events are disjoint. So if we're asking for the probability of one event or another, for example, what's the probability of getting heads or tails, then what we do is we take the probability of each event and we just add those two probabilities together. And we're looking for basically this kind of a terminology of OR, where the OR is going to give us an idea that we need to add the probabilities. And we'll have an example here where we're going to be able to use this special addition rule where events are disjoint. So in this example, this is a probability model. We could check, of course, and make sure that this is an actual probability model, just being sure that they all add up to 1, for example. And we can tell right away that none of them are negative or greater than 1, so it looks viable to me. But these are the distribution of doctoral degrees. Now, we want to find the probability that a randomly selected doctoral candidate earned a degree in physical science or life science. Now, we have to kind of infer here, because life science and physical science, these are different things, and so there's really no chance that a doctoral candidate is going to be getting their doctoral degree in two different subjects at the same time. It's going to be either one or the other, and so these would be considered disjoint. Nobody is getting both of these degrees. They're either getting one or the other, and so the probability of physical science or life science is just going to be the sum of these. It's going to be the probability of getting the physical science degree plus the probability of the life science degree, and so it's going to be 0.100 plus 0.171, and that's 0.271. And then we can have more than just two. For example, we want to find the probability that a randomly selected candidate earned a degree in one of these three things: physical science, or life science, or math. I said three, actually four things, or computer science. And so it's the probability physical science, or life science, or it could have been math, or it could have been computer science. And since each one of these are disjoint, because we also had math over here and we have computer science, we can find this probability just by adding them. We would add up all four, and so in this situation we want to add up the physical science probability plus the life science probability plus the math probability, which is 0.028, and then plus the one for computer science, 0.026. And I'm going to add up those on the calculator here, and that gives us 0.325 as the probability for this combination of events. And then what about, is a doctoral degree in math unusual? Can you remember what it means, unusual? There's this general standard that we have for something being unusual. The probability for the math degree, so probability of math, we already have it from the table, is 0.028. Is it unusual? Of course we should compare it to what value? And the correct value is 5%, which is 0.05. And since it's less than 0.05, yes, it is unusual to get a doctoral degree in math according to this table. Now it's pretty straightforward, this special addition rule, but we're going to introduce a new idea here, which it's unrelated to the addition rule in general. It's just a fancy terminology that we use when we're talking about events, and especially when we're talking about sets. But we're about to start doing this other thing where we draw Venn diagrams, and that also lends itself to helping to illustrate this idea of a complement of an event. Now remember, we had this thing called the sample space, which is all of the possible outcomes that there are for the whatever situation we're talking about. Now the complement of a specific event, it's just the collection of all of the outcomes that are not part of this event. And so, for example, the complement of flipping and getting a heads would be getting a tails, but we can have a more complicated version of finding a complement. It's not always so easy as that, and we'll see a couple of examples here in a moment. But complementary events, you can always tell if events are complementary because they should be, for one, they should be disjoint. And then if we add up the probability for complementary events, the probability should be 1, because you have an event and then you have all of the other outcomes that are not to do with that event. That would end up making up the whole sample space. And the probability of getting something out of the sample space is just going to be 1. And then we've got a couple of things here, just building on the idea that the probability of the complement of an event, which the complement we always write with this little C as kind of a, looks like in the exponent position, this little superscript C means the complement of E. If we add the probability of an event with the probability of the complement, we should get 1. And then there are just 3 different ways that we can organize that same equation and end up with these different rules, but they're all really the same rule, just that they add up to 1, the probability of an event with the complement. And so what about this? In reality, when a baby is born, the probability to get a boy is 0.512, so what's the probability of having a girl? Well, obviously, having a boy and having a girl, those are complementary events because they're disjoint, and those are the only 2 things in the sample space. And so the probability of getting a boy plus the probability of getting a girl, these should add up to 1. And since the probability for getting a boy is 0.512, then the probability of getting a girl would just be the difference between that and 1, which is 0.488. Now we see here a picture of how we can use Venn diagrams to understand this idea of the probabilities. Notice these 2 Venn diagrams, and the areas here, we could count the area of this circle as the probability of event E, and then we could count the area of the purple circle as the probability of event F happening. And then the total area, what it's talking about is the total area of the rectangle altogether. Now these ones, they would not be complementary events because the probability of E and the probability of F, they don't end up making up the whole rectangle. But if we take the probability of E, its complement would be everything outside of E. So it would be the stuff that's not to do with F, that's all on the outside, that'd be just the blank background stuff, but then also F. And so this would make up all of the complement of E. It's the event F and then also everything that's not F or E. And now we don't always have disjoint events. We can have sometimes where these events, they have something in common, somehow they overlap a little bit, and that's what we're going to have to get into here, because whenever we're trying to find the probability, remember we were talking about in general for the addition rule, the probability of E or F. Now you can understand whenever we're finding for disjoint events, the probability of either E or F, we just want to take these 2 areas and add them because they don't overlap at all. But if we take these areas that overlap, if we add these areas, then this little part that's in the middle, we would end up counting it twice. And so that's how we will develop the general addition rule, which is where we have to subtract 1 copy of this little slice in the middle. But more on that to come later. We want to try this example just by our own intuition, trying to figure this one out. Suppose you've got a bag of chips, not potato chips, but more like gambling chips, I guess, that they're numbered 0, 1, 2, 3, 4, and 5. And then event E is going to be the event that you choose a number less than 3 whenever you draw a chip out of this bag. And F is going to be the event choose a number that's greater than 3. So the probability of E or F, we have to think about whether these events are disjoint or not. Choosing a number less than 3 or choosing a number greater than 3. Can those ever happen at the same time? It doesn't seem like it. So actually we can just use this special addition rule, which is that we add these probabilities together. And the probability for E to choose a number less than 3, the numbers that are less than 3, notice that there are 3 of them, 0, 1, or 2. So the probability for that, it should be 3 out of 6. And then the probability to choose something greater than 3, there's 2 options for that. There are 4 and 5 are greater than 3, so that's 2 out of 6 probability. This would become 5 out of 6, which if we try that one in the calculator, because we want to round, of course, to 4 decimals, so it's going to go 0.8333. Now what about these 2 events? If we want to do another kind of a situation for P, the probability of E or F, we're going to have the event that's going to be choose a number less than 4, and then we have another event, choose a number greater than 2. Now you can choose a number that's less than 4 and a number that's greater than 2 at the same time, and so that's where we're getting into an issue because these are not disjoint events. Choosing a number less than 4, choosing a number greater than 2, they're not disjoint. And so what we can come up with this probability of either something less than 4, which is E, or something greater than 2, which is F. If you think about it, this probability for E, this one is already the probability of getting, which one? Something less than 4, so either a 0, or a 1, or a 2, or a 3. And then the probability for, see, we're going to add them. The probability for F is going to be the probability of getting something greater than 2, so either a 3, or a 4, or a 5. Now, if we add these probabilities together, you notice that we're going to take a probability twice, because the probability of getting a 3, getting a 3 is already part of event E, and getting a 3 is part of event F as well. So we need to subtract the probability of getting a 3. So we don't want to count it twice. It's already happening here and here. So we should subtract the probability of getting a 3. That way we're only going to count it once, and then this should end up working out for us. Now if you just think about it, what the probability is going to be to choose a number less than 4 or something greater than 2, that's actually all of the chips in the bag. Every chip that's in here is either less than 4 or it's greater than 2, so there should be a 100% probability. If we simply added these without taking into account that we're counting the probability of drawing a 3 twice, then we would end up with a probability that's more than 100%, and of course that's not allowed. But this way it should work out. So the probability for E, this was 4 different things, so this should be 4 out of 6. The probability for F, it was 3 things, so this was 3 out of 6. But then we're going to take away the probability to get a 3, so it's going to add up. Now it becomes 6 out of 6, which is just 100%, or else 1 as the probability. And that gives us sort of the idea, the mentality behind the general addition rule, which now this works even if an event is not, or even if an event is disjoint. The general addition works because the probability of 2 disjoint events happening is just 0, so you're just not going to subtract anything. But if events are not disjoint, then now the general addition rule comes into play big time, because we're going to get the wrong answer if we fail to subtract the probability of where they overlap. And we'll see it in an example here. And we're finding the probability that a student in this shop class, notice there are 30 students, we have how many people built birdhouses, how many built mailboxes, and how many built both. We want the probability that somebody built a birdhouse or a mailbox. And certainly it should just be 1, because that's the only things that are possible to build. So it seems like maybe there's a chance that somebody didn't build anything. But we can just calculate this one instead of guessing about it. You know, these numbers, just looking at the numbers, maybe it's not immediately obvious, so we'll just carry on calculating this one. But we have that 22 built birdhouses. I'm going to draw, this is going to be all of the things that we could have built. So maybe somebody built a shelf or something. But anyways, there are 22 people who built birdhouses. So that should be the area of this circle is 22. And then there were 12 people who built mailboxes. So that should be the area of this circle is 12. But then we already know that 5 people built both. And so there's this kind of area in between, which makes up 5. And so to get this area that's hanging out on both of these, you see the area that's here, it should be the whole area of the circle, which was 22, but then minus the 5. And so this area should be 17. And then we have another area, which is this piece that's outside of where they overlap. We know that the whole circle together is 12, so this should actually just be 7 that is here. And then the probability of building a birdhouse or a mailbox, that's going to become, you notice since they're not disjoint, what we're going to have to do is it's going to be the probability of the birdhouse plus the probability of a mailbox, and then subtract the probability that it's both. Now the probability of a birdhouse, this one, it should be basically just the whole circle is the probability of a birdhouse is all the people who built a birdhouse, that's 22. 22 out of 30. And then how many people built a mailbox? That was 12 out of 30. And then the probability of both, that one is, basically there were 5 people who built both, so that one's 5 out of 30. And then if we add these all up together, that's going to be 34 minus 5, so it looks like 29. 29 out of 30, which 29 out of 30 as a decimal, we'll get it going here, is going to be 0.9667. So there was just one person who built neither. But anyways, that's how we'll use the general addition rule. And that does it for this section 5.2 video. I hope it was helpful, and I'll catch y'all in the next one.